Welcome to the live interaction session of week 8 of our course Computational Fluid Dynamics by Professor Srinivas Jayanti from Department of Chemical Engineering, IIT Madras. I am your TA Manjunathan from Department of Applied Mechanics, IIT Madras. So let's start our session for today. So in week 8, the solution for the incompressible flows, that is the solution of Navier-Stokes equation for incompressible flows, were discussed, where how some techniques used in compressible flows can be used for solving incompressible flows, as well as the velocity pressure coupling methods were discussed in detail. I hope you have each watched the videos. So let's start our interactive session. So I'll be displaying some questions for you to revise and recollect the content of this week. And after some time, you can take some time to understand the question and kindly inbox your answers. So first question, in the context of artificial compressibility method, a key parameter is dash. Options are option A, Reynolds number, option B, Mach number, option C, artificial density, option D, Prandtl number. So in the context of artificial compressibility method, which one among the following is a key parameter? So the question is, in the context of artificial compressibility method, which among the following is a key parameter? So the question is, hope I am audible. The question is, in the context of artificial compressibility method, which among the following is a key parameters? Options are option A, Reynolds number, option B, Mach number, option C, artificial density, option D, Prandtl number. Please inbox your answers. So the answer is option C, artificial density rho star. So this artificial density rho star is a non-physical or created fictitious parameter, which is introduced in the modified equations to control the control the values to get a better convergence in the incompressible solution. So normally we use del dot u is equal to 0 as continuity equation, but in artificial compressibility method, this dou rho star by dou t plus del dot u is taken as is being taken as our continuity equation, where this rho star is the artificial density. Again, this rho star is nothing but rho star is E by beta, where beta is a fictitious compressibility factor. So this is the key parameter used in uh, artificial compressibility method or artificial density. And this term, this dou rho star by dou t, this term is uh, continually iterated to reach a steady state. That is, its time-related fluctuations uh, should die down uh, in the iterations, and a pseudo loop is pseudo time loop. In this pseudo time loop or pseudo time iterations are run to eliminate this state, so as to get a proper stability and convergence to our incompressible problems. Moving on to next question. The primary purpose of artificial compressibility method in CFD is to which of the following? Options are: option A, directly solve compressible flow problems. Option B, introduce a fictitious time derivative for pressure. Option C, eliminate the need for pressure velocity coupling. Option D, model real world effect of compressibility in fluids. So the question is on what is the main purpose of artificial compressibility method in CFD. Please inbox your answers. Yes, we have seen while discussing the previous problem itself, we have expressed that the equation is for solving incompressible flow problems. So option A is wrong, and option B is our right answer. Introduces a fictitious time derivative of pressure. That is, it introduces dou by dou t of rho star, where rho star is equal to p by beta square. So, in turn, if you substitute this p by uh, beta square in the equation, then it will be 1 by beta square is constant. So 1 by beta square into dou by dou t of p. So that is what meant, meant by this option. That is, introduces a fictitious time derivative of pressure. Even though there is no change in with respect to time, uh, this fictitious time derivative can be introduced to introduce that, then solved in a pseudo time loop to get better stability. And this beta can be controlled by the uh, process, or we can control the values of this beta as a corrector or correction measure for achieving better stability. Yes, same there is this explanation of our answer, that it needs a pseudo time derivative of pressure, and by introducing this pseudo time derivative of pressure, it allows the incompressible problems to use well-established time marching algorithms that is normally used in compressible flow simulations. Next question. Compared to the traditional pressure-based solvers for incompressible flows, the artificial compressibility method is, options are, always achieves faster convergence. Option B, may require additional computational sources. Option C, inherently less accurate. Option D, cannot handle unsteady flow simulations. So the question is uh, comparing traditional pressure-based solvers for incompressible flows with the use of artificial compressibility for solving incompressible flows. So which among the following is true regarding the comparison? It's a pretty easy question. So that we have seen that from previous two questions, that for artificial compressibility method, a pseudo time loop is needed. So this pseudo time loop will increase or will require more or extra computational resources. So our option answer is option B. That is may require com- additional computational resources. Moving on to next question. Which of the following statements about artificial compressibility method is false? So the question is asking you to find a false statement among the following regarding artificial compressibility method. Options are option A, it requires careful selection of artificial density parameter. Option B, it can be used with various discretization schemes like finite volume methods. Option C, it eliminates the need of solving separate pressure equation. Option D, it is a popular approach for simulating turbulent flows with incompressible conditions. Options are it requires careful selection of artificial density parameter. Option B, it can be used with various discretization schemes like finite volume methods. Option C, it eliminates the need for solving a separate pressure equation. Option D, it is a popular approach for simulating turbulent flows with incompressible conditions. Try to answer the question. You can inbox your answers. Our answer is option C. The answer is option C. Because it is stating that it eliminates the need for solving a separate pressure equation. Uh, no, it is false because uh, we do need uh, there is a requirement for solving separate pressure equation, but even though we are taking dou by dou t as rho star is equal rho star is equal to 1 by beta square dou by dou t of p. So this equation has to be solved. So it do require solving a separate pressure equation. Whereas this the careful of selection of artificial density parameter is that is this rho star that will depend on this beta, and that a careful selection of that artificial density parameter is required because tweaking that parameter we can give a better stability to the system. And this pressure, this beta square dou p by dou t, this term is iteratively solved in a pseudo time loop. So why it is called pseudo time loop? Because this is a loop within a loop. This uh, time loop has to be uh, iterated to a point where this dou p by dou t is becomes zero. That is, the- in such a case only it will become incompressible. It will become an equivalent flow, equivalent incompressible flow. So that loop has no other outcome rather than to give the system a proper stability, give the overall iteration a proper stability. And this step is carried out at each iteration of the for each mm, main iteration of the Navier-Stokes equation. A inner loop of this pseudo time loop will pseudo time loop has to converge or has to have to be eliminated. Moving on to next question. A limitation of artificial compressibility method for some application is. So the question is asking limitation of the artificial compressibility method. So which of the following is a limitation or can be a limitation of artificial compressibility method for some application, not for every application, for some application. Options are: option A, difficulty in handling complex geometries; option B, potential issues with interface capturing in multiphase flows; option C, inability to model heat transfer phenomena; option D, incompatibility with existing CFD software packages. So, which among the following is a limitation of artificial compressibility method in some particular applications? Try to answer the question. Our answer is option B, that is, artificial compressibility method has potential issues with interface capturing in multi-phase flows. That is our answer because when there is multi-phase flows, that is, when there is more than one phases existing inside our computational domain, then artificial compressibility methods will struggle to converge, or the pseudo time loop will create issues uh, at these boundaries, as it won't be easy to easy for the inner pseudo time loop to get converged. So in such cases, uh, artificial compressibility methods will have to struggle. So it is not suitable for solving struggles. I mean, sorry, it is not suitable for solving flaws with multi-phase where uh, the interface between the fluids is more evident. Moving on to next question. Which terminology best describes the role of artificial compressibility method in CFD solvers? So the umbrella term or the category of artificial compressibility method is being asked in this question. So which terminology best describes the role of artificial compressibility method in CFD solvers? So what is the role of artificial compressibility method in CFD? Options are option A, turbulence modeling approach, option B, preconditioning technique, option C, direct numerical simulation method, option D, boundary condition treatment. So, what is the type of what is the type which we can give to the artificial compressibility method in context of its application in CFD? Try to answer the question. The answer is option B, that is preconditioning method, because this pseudo time loop has to be converged uh, before moving on to our main simulation, and this for every major simulation of the main equations, this pseudo time loop has to be converged for the simulation to run, simulation to have stability. So this artificial compressibility method mainly comes under preconditioning methods or preconditioning techniques. For simply saying, artificial compressibility method is a preconditioning technique which essentially transforms the incompressible system of application into a form that can be efficiently handled by established algorithms for compressible fluid flows. Moving on to next question. When using artificial compressibility method, a good practice is to options are option A, set the artificial density to a very high value. Option B, continuously monitoring the pseudo time convergence process. Option C, utilize explicit time marking schemes exclusively. Option D, ignore the influence of artificial density in the final solution. So the question is asking, when using artificial compressibility method, which among the following will be a good practice to follow? Options are setting the artificial density to a very high value. Option B, continuously monitoring the pseudo time convergence process. Option C, utilizing explicit time marking uh, explicit time marking schemes exclusively. Option D, ignoring the influence of artificial density on the final solution. You can inbox your answers. Answer is option B, that is to continuously monitor pseudo time convergence process, because uh, the pseudo time loop should converge smoothly and faster. Then only our overall simulation time will proceed. So it is best to monitor the pseudo time convergence process. Uh, and if there is some issue, then we will have to tweak the beta parameter for the artificial compressibility factor parameter to get better uh, convergence of this pseudo time loop. So while using artificial compressibility method, one have to uh, keep track of the pseudo time loop convergence, because if it is not happening, or if it is getting truncated, or the loop is getting exited due to the tolerance limit set by the user, then there are chances that some influence of this artificial compressibility, that is uh, introduce the fictitious parameters effect will remain in the final solution. So to avoid that, the user have to continuously monitor the pseudo time residuals or convergence. Next question. What are some limitations of artificial compressibility method? Options are: option A, it can be computationally expensive for complex geometries. Option B, it may not be accurate as dedicated incompressible solvers for all flow regimes. Option C, it requires significant user expertise for proper implementation. Option D, all of the above. So, which among the following are limitations of artificial compressibility method? You can inbox your answers. So, all the options are true. That is option D, all of the above. It is true that not just artificial compressibility, almost all the methods will be computationally expensive for complex geometries. Next option, it may not be accurate as dedicated incompressible flow solvers for all flow regimes, and it is best suited for internal flows. So suppose our flow regime is uh, inside tube or duct, that kind of flow regimes, then artificial compressibility method may not be best suited for uh, internal flows. Right? So in such, uh, sorry, not best suited. It is not best suited for internal flows. Whereas for external flows such as aerodynamics calculation or some flower mud body kind of calculations, this artificial compressibility method works well. Option C, it requires significant user expertise for proper implementation. Yes, because tweaking the artificial compressibility parameter or artificial density parameter requires skills, because if the pseudo time loop is taking time to converge or it is not converging properly, then it should be adjusted properly so as to get uh, a better, stable and faster simulation process. So all of the options are limitations of artificial compressible method. Moving on to next question. In a collocated grid, which variable is typically stored at same location? So the question is, uh, in collocated grid arrangement, which of the which pair of variables or which set of variables are normally or typically stored at the same location? Options are: option A, pressure and velocity; option B, pressure and density; option C, velocity at all directions; option D, none of the above. So, which among the following which among the following variables are normally stored at same location while using collocated grid arrangement? You can inbox your answers. Our answer is option A, pressure and velocity. This collocated grid arrangement uh, all is a method for pressure velocity coupling. In collocated grid arrangement, the pressure and velocity will be stored at the same location in the grid. But the collocated grid uh, method of storing velocity and pressure at the same location or same grid points can lead to decoupling issues. And it is a less efficient method of uh, velocity pressure coupling. Next question. A staggered grid arrangement is primarily used to address which challenge in CFD simulation. So the question is on what's a staggered grid arrangement, or where is the staggered grid arrangement primarily used? Options are option A, turbulence modeling, option B, heat transfer calculation, option C, pressure velocity coupling, option D, grid generation complexity. So which of the following challenges is being managed by staggered grid arrangement in CFD? You can box your answers. Our answer is option C, pressure velocity coupling. So, like to overcome the collocation grid issues, the alternative is a staggered grid arrangement. So, staggered grid arrangement is used to overcome or solve the velocity pressure velocity coupling issue in the CFD, where in staggered grid, pressure and velocity will be uh, kept as in staggered conditions. That it is located in alternate sets. If you can similar kind of, it will be an alternative arrangement of storing pressure and velocity. Because uh, while using collocated grid arrangements, there will be oscillation issues will be developed due to the collocated grid arrangement. Staggered grid arrangement will be preferred. Next question. In the context of pressure correction methods like simple, it's an algorithm, it's a name of an algorithm, simple algorithm. What does the P represent? So, what is the P in simple algorithm that is being used in CFD? Options are option A, initial guess for pressure, option B, pressure at the next time step, option C, corrected pressure value, option D, pressure difference between neighboring cells. says symbol is an algorithm, and what does the P in symbol represent? Okay, our answer is option C, corrected pressure value. So this symbol algorithm is short form for semi implicit method for pressure linked equations. So this is the P or pressure. So this method is developed by Professor Patanger and Spalding. And this method very well works with the pressure coupling. It solves the pressure coupling problem very well. And this in this method, the use of a corrected pressure term is being used. So that corrected pressure is used to link between the equations. So that's why the question is asked. And also there's a another algorithm called simpler, which is symbol revised. Revised symbol is called simpler. That is developed by Patanger. So hope that uh, explains it. Moving on to next question. Next question. Which interpolation scheme is commonly used in staggered grids to determine the phase velocity of the pressure equation? So, which of the following interpolation schemes is commonly used with staggered grids to determine phase velocities for the pressure equation? Options are option A, central differencing, option B, upwind differencing, option C, Riccio interpolation, option D, least squares method. So the question is asking which of the following methods are used to determine the phase velocities in staggered grids. Our answer is option C, Riccio interpolation. So uh, from the options itself, there is a giveaway like this interpolation word is only found in this option, interpolation. Okay, this Riccio interpolation uh, is used in velocity coupling, whereas to reduce this checkerboarding or uh, pressure oscillations, not pressure oscillations, the checkerboarding of the checker, to avoid the checkerboarding pattern. Also, in Riccio interpolation, this this is our core domain. These are cell centers. Then here, mostly in CFD, we will be taking center to center values. Uh, in cell volumes, we will be taking in control volume method, we will be using mostly this center points. We will be calculating our velocities. But while calculating pressure, taking this center velocities uh, will create some numerical issues. That's why Ree and Chow proposed taking velocities at the walls or midway. This is so this will be midway of the velocities or phases of the cells. So such an interpolation method is called Riccio interpolation. Next question. A key advantages of using staggered grid in incompressible CFD simulation. The question is asking advantages of using staggered grid in incompressible CFD simulation. Options are option A, reduced computational cost. Option B, improved accuracy for turbulent flows. Option C, easier implementation of boundary condition. Option D, enhanced convergence for pressure velocity coupling. From the understanding of previous question, you can simply answer the question. Try to answer the question. What is the key advantage of staggered grid in incompressible CFD simulation? Option or answer is option D, enhanced convergence for pressure velocity coupling. We have already discussed that staggered grids are methods used for pressure velocity coupling, and in staggered grids, this pressure and velocity will be stored in separate grids, which will eliminate the chances of creating checkerboard effects, and also it will lead to a more stable and efficient solution of pressure equation. Next question. Which of the statement is false regarding pressure equations in incompressible CFD? Options are option A, it can be derived from the continuity equation. Option B, it involves the equation of state for the fluid. Option C, density is treated as a constant variable. Option D, it plays a crucial role in capturing shock waves. Options are, the question is on which among the following is a false statement regarding the pressure equations in compressible CFD. Options are, it can be derived from the continuity equation. Option B, it involves the equation of state for the fluid. Option C, density is treated as a constant variable. Option D, it plays a crucial role in capturing shock waves. So which among the following is a false statement? Try to answer the question. Our answer is option C, density treated as a constant variable. Moving on to next question. When using a finite volume method for pressure equations, what represents a control volume in a staggered grid? So the question is on a representation of control volume in a staggered grid for pressure equation. Options are option A single grid point. Option B, the entire computational domain. Option C, the cell surrounding a pressure point. Option D, the space between the neighboring velocity points. So the question is how pressure equations are represented in a control volume method in a staggered grid. answer is option C, a cell surrounding a pressure point. The finite volume method discusses the governing equation over control volumes, and in staggered grids, the pressure equation applies to the cell surrounding a pressure point. So, if you are taking the scalar quantities like pressure, temperature, etc. are uh, expressed as points in the cell and velocities as arrows. Velocity will be arrows. And this pressure equation is calculated at the surroundings of this point. So this is the point. So it will be calculated in the surroundings of the point. So this is the representation. Moving on to next question. A disadvantage of using staggered grid compared to collocated grid can be. Question is comparing staggered grid and collocated grid and asking for the disadvantage of staggered grid over the collocated grid. Even though staggered grid is uh, computationally efficient and gives stable pressure velocity coupling, what is the disadvantage of the staggered grid over collocated grid? Options are option A, increased memory requirements, option B, simpler implementation of source terms, option C, more complex interpolation procedures, option D, improved stability for high Reynolds number flows. So which of the following is a major disadvantage of using staggered grid over collocated grid? Our answer is option C, or complex interpolation procedures. We have seen that Richo is a interpolation method used with staggered grid. So such interpolation procedures are required for staggered grids to maintain consistency and to achieve better stability. While these interpolation procedures will give better consistency, it will add complexity to the schemes compared to those of collocated grids. Moving on to next question. Which of these term is not typically present or typically included in pressure equation for incompressible CFD? Options are option A, pressure gradient time. Option B, convective velocity time. Option C, viscous stress time. Option D, source time. So, which of the following times is not typically included in a pressure equation for incompressible CFD? Our answer is option B, convective velocity time. Convective velocity time is not included while calculating the pressure equation in an incompressible velocity time. Moving on to next question. The pressure equation in incompressible CFD is derived from which governing equation? The question is, which of the following equations forms the basis for pressure equation in an incompressible CFD? Options are option A, energy equation, option B, continuity equation, option C, momentum equation, option D, ideal gas laws. answer is option B. We have already discussed that in the earlier while discussing artificial compressibility method. The equation is first equation is mostly taken from continuity equation. Moving on to next question. In a staggered grid, pressure is stored at. So the question is asking the location of the pressure. So in a staggered grid, where is the pressure located at? Options are option A, cell faces, option B, cell centers, option C, vertices, option D, it can be anywhere on the grid. So we have discussed a similar question earlier. Try to reflect and answer the question. The answer is option B, cell centers. We have already discussed that. The pressure will be located at cell centers, whereas velocity will be represented at the faces. Moving on to next question. Which of the following is an advantage of using staggered grid? We have discussed many of them. So the question is asking again, which of the following is an advantage of using staggered grid? Option A, simpler implementation of boundary condition. Option B, easier to calculate the gradients. Option C, requires less memory storage. Option D, more intuitive for visualization. So which among the following is an advantage of using staggered grid? Our answer is option B, easier to calculate gradients. So while using staggered grid, it will be easier to calculate the gradients of velocity. Moving on to next question. In a pressure velocity coupling, the issue arises in CFD due to which of the following? Options are option A, non-linearity in momentum equation, option B, turbulence modeling, option C, incompressibility constraint, option D, high Reynolds number flaws. So from where did the requirement of or pressure velocity coupling issue arises in a CFD? Options are nonlinearity in momentum equation, option B, turbulence modeling, option C, incompressibility constraints, option D, high Reynolds number flaws.